Zarya's beam is 2,002,147.5 degrees Celsius. And I know that because Zarya's beam is pure white, and for something to burn so hot that it emits a white glow, it would have to be 6,000 degrees Celsius. There's lots of questions surrounding the science of Overwatch characters and the implications of their kits, such as Zarya's graviton surge, for example. That's not really a black hole, is it? I mean, it would weigh the equivalent of 27 Earths at that size. It would rip apart the planet before spiraling towards the sun. And even if in the Overwatch universe singularities form at far lower densities, it still doesn't have a gravitational pull while airborne. It can't be a black hole. We can't just trust what's placed before us, we have to investigate. So before we can answer how hot Zarya's beam is, we have to ask what even is Zarya's beam. Throughout Overwatch, Zarya's weapon is referred to as a particle cannon. This narrows it down a little bit because we can rule out things like an electrified water blaster or a pink flamethrower simply because they don't fit the description. Unfortunately, this also rules out plasma as an option, which feels weird because plasma is the most visually accurate answer, and I'm sure that's what most of you thought Zarya's beam was made out of as well. A particle cannon is a weapon that uses magnets to accelerate a beam of charged particles to high speeds. Unfortunately for me, a particle cannon doesn't do damage based on its temperature. Instead, a particle cannon does damage based on its kinetic energy, meaning the faster the beam moves, the more damage it does. We still haven't proved that Zarya's weapon is a particle cannon beyond the name itself, but isn't plasma made of particles? Could you also call a plasma cannon a particle cannon? Well, to do so, we would have to prove that Zarya's weapon isn't a charged particle cannon, and we can do that with light. Because a charged particle cannon isn't actually visible by itself. It needs to go through a medium and interact with other particles in order to be seen. This works fine in most situations since the atmosphere is a medium that would allow the beam to be visible, but there is one map called Horizon Lunar Colony, a scientific research base situated on the moon. And when we go outside the station into the vastness of space, Zarya's beam is still visible despite no medium for it to interact with, meaning the beam itself must be visible, and thus can't be a particle beam. The other more obvious kicker is that a charged particle beam wouldn't taper off and stop after 15 meters. Charged particle beams can have the speed and power to travel planetary distances in a fraction of a second. The particles are also very small, and the atmosphere is nowhere near dense enough to impede the travel of these particles. So whether it's the visibility of the beam in a vacuum or the 15-meter range, we have to say that Zarya's beam can't be a charged particle cannon, and instead must be a plasma cannon. Now that we've confirmed what the beam is made out of, we can work on deciphering its temperature. As mentioned at the start of the video, if we look at the pure white color of the beam, we can say that it's burning at 6,000 degrees Celsius. This is because as objects get hotter, they emit higher and higher frequencies of light. This is a phenomena called blackbody radiation. Another way that we can test the temperature of Zarya's beam is by doing an in-game experiment. And after shopping around for a while with different ideas, I've decided to focus on these destructible concrete railings because they don't break how you would expect concrete to break. Normally, if you take a sledgehammer to a block of concrete, it will come off in chunks from where the sledgehammer hit. But that doesn't happen in Overwatch. Instead, the concrete railings shatter into a million pieces at once. And the only way concrete could break in such a fashion would be if the water content inside the concrete suddenly boiled and created pressure-induced breakages. With this idea in mind, we could figure out the temperature of Zarya's beam based on how quickly it boils the water inside these railings. First, let's figure out how much water is inside these railings. Tracer is 162.5 centimeters tall, and by measuring her at different angles against the railings, we can measure the height of the concrete pillar as 92.5 centimeters tall. Once we know the height of the pillar, we can work out the length and depth of each concrete segment, allowing us to get the total volume of the concrete railing at 0.358 meters cubed. Concrete typically has a weight of 2,400 kilograms per meter cubed, so we know that the weight of this concrete railing must be 860 kilos. If we assume a water content of 0.4%, we can safely say that there is 3.5 kilos of water total in this concrete railing. The energy required to boil 3.5 kilos of 30 degrees Celsius water is 1 million joules. It takes Zarya 1/60th of a second to break one concrete railing and thus to output 1 million joules. This means that her beam has 60 million watts or 60 megawatts of energy, assuming zero energy is lost and that the concrete and her beam have a perfect conductibility. Unfortunately, this doesn't help us calculate the temperature of the beam, since all we've done is calculated the minimum power of Zarya's weapon itself. In our calculation, Zarya's beam is a perfect conductor of heat, so all the 1 million joules produced from her weapon aren't being transferred into heating the plasma, but instead into heating the water. Unfortunately, I don't know how to calculate the thermal conductivity of plasma to define a temperature that transfers 60 megawatts of energy. It's something that stumped me while researching this video, in fact, sifting through scientific papers and complex equations that I couldn't understand. All hope isn't lost though. Since we know the energy output of Zarya's weapon itself, we can use another method to calculate the heat of Zarya's beam. If we know the energy required to heat up our plasma by given amounts and the mass of plasma in Zarya's beam, then we can calculate how much our plasma would heat up from a 60 megawatt power source. Figuring out plasma's thermal capacity, aka the amount of energy that is required to heat it by a given amount, is very difficult. A quick Google search doesn't give you an answer, and sifting through scientific papers is something that is far out of my depth. So I think it's easier if I just pick a number that seems roughly accurate and don't think too hard about it. Something like 10 calories per degree increase in Celsius per gram of plasma, a thermal capacity that is roughly 4 times higher than that of hydrogen gas. To get the mass of plasma in the beam, we can calculate the volume by measuring the height and depth of the beam against the 15-meter length. Doing this gives us a volume of 0.073 meters cubed, and if we assume a plasma density of 5 grams per meter cubed, we get 365 milligrams of hydrogen plasma comprising Zarya's beam. 365 milligrams of hydrogen plasma heated by 60 megawatts at 10 calories per Celsius gram will get 800,859 degrees hotter. But this system only gives us the rate of heating. It doesn't tell us the plasma's actual temperature, since if we left this beam on for 1 second, it would be 800,000 degrees, but if we left it for 2 seconds, it would be 1.6 million. Zarya can only fire for 5 seconds at a time before reloading, so if we assume that Zarya's beam doesn't change temperature while she's firing, then we can get a fixed average temperature by multiplying 800,859 by 5/2, giving us our final temperature of 2,002,147.5 degrees Celsius. This is so hot that it would immediately irradiate everyone in the vicinity from the light produced alone. This isn't a plasma beam, it's a cancer beam. Looking at the plasma beam instantly blinds you. In fact, even if you're looking away, it probably still blinds you. Zarya's beam is so hot that it ignites the nearby atmosphere and is so bright that for the 5 seconds that she's shooting her beam, everything to the horizon is lit up brighter than the midday sun. Her beam sustains a temperature that is comparable to the center of brown dwarfs, aka failed stars, so not quite hot enough for fusion, but not very far off either. I'm kind of lying, sorry, because it depends. I've made so many assumptions along the way that our 2 million degree number is likely just incorrect, especially because our method of calculating the temperature is flawed, to say the least. Because there's another way to calculate the temperature, and it's using the Stefan-Boltzmann law. This law is used to calculate the energy of radiation emitted from an object. It's the same thing used at the start, where we use the color of Zarya's beam to measure its temperature, except this time we know that the beam is running on 60 megawatts of power minimum, which means that it's also emitting 60 megawatts of radiation to stay at a thermal equilibrium. We can work backwards from that by finding the surface area of the beam and its emissivity to calculate its temperature. The plasma beam likely has an emissivity close to that of the sun, so let's settle with 0.95, which is to say that it's highly efficient at releasing its energy as heat. The surface contact of the beam with the concrete is about 36 centimeters squared, meaning that at least 60 megawatts of energy is being transferred from the tip of the beam to the mass of the concrete. And the temperature of a highly emissive material to produce 60 megawatts per 36 centimeters squared is 23,311 degrees Celsius. Much colder than before, about 4 times that of the surface temperature of the sun and about half that of a lightning strike. Previously, I said that I couldn't calculate the thermal conductivity of plasma to define what temperature it would have to be in order to output 60 megawatts of power. But now I have something even better. Since we know the thermal conductivity of concrete, we can calculate how hot this end of the concrete would have to be in order for this end of the concrete to reach 100 degrees Celsius in 1/60th of a second. This negates our previously flawed assumption of the concrete having perfect thermal conductivity while directly calculating the beam temperature, because whatever temperature this end of the concrete is would have to be equal to or less than the temperature of the beam itself. So if we clock the base temperature of the concrete as 30 degrees Celsius with an average cross-sectional area of 0.425 meters squared, and then plug in our thermal conductivity of concrete, which is 1.046 watts per meter Kelvin, we get the beam temperature required to take our 1 million joules and transfer that over the 2.8 meters of concrete in 1/60th of a second. Doing so gives us a beam temperature of 377,155,964 degrees Celsius. Zarya's beam is now 4 times hotter than the core of a blue supergiant. Earth is now clearly visible from other planets, rivaling the brightness of our sun. The local atmosphere explodes while the heat melts everything into a giant plasma lake. The light from the beam is reflected by the atmosphere and blinds people hundreds of kilometers away. It is a planetary catastrophe. I did try to find someone with a comprehensive knowledge in thermodynamics and physics to help do the calculations and peer review my logic, but I couldn't find anyone, so here we are now. Depending on how you work it out and how many assumptions you make, Zarya's beam is either 6,000, 23,000, 2 million, or 380 million degrees. And the biggest issue is that the concrete isn't breaking from steam expansion, it's just really brittle. Punching, shooting, kicking, it all breaks the concrete in the exact same way, it's just cheap concrete. If you enjoyed the video, make sure to leave a comment about what you might like to see next. This one was particularly maths heavy. I don't plan on making them all so condensed like that. Stay tuned for another stats video. I have something planned for when Space Rangers released, keep an eye out. And thanks for watching.